Hello, everybody. Good evening. How was your weekend?
Good morning.
Wait a couple minutes for folks to get here. What did you think of the up until this point, we've been talking about global averages, right? We've been talking about how the global surface temperature has increased. We've looked at climate models where we're looking at the whole planet and all of the sunlight coming down, how much that's going to heat up our radiative body, how much that emits in infrared, and how much is reflected back onto the surface, causing additional warming. And so we've been looking globally, right? And so it's really easy to kind of just think in these small numbers. Oh, we're getting a 1.1 degrees Celsius change in average temperatures. When in actuality, what we see on the ground in different places can be very, very, very different. Okay, I'm going to go ahead and shut off some of those external sounds. And what I liked about Dr. Farous's lecture is it's starting to bring in the idea of geography into our planet, because, if all we do is ever talk about in global averages, we'll never really get differences in climate systems from one region to another. And so I think hers was a really good introduction into the different climate zones that we have and the different range in types of climates that we have. So we're learning a little bit about the classifications that have been used, and those will be important when we talk about, what kind of changes will we see on the globe. We're not just talking about what's the average change globally, but also what's the specific effect in different regions, because it's not all going to be evenly divided, right? We've already seen that with warming, there's more warming in the northern hemisphere than there is in the southern hemisphere, because there's more land, less reflective surface. And so you would expect, since land is darker than white, it would absorb more. And so we get more heating in one region versus another. And that's going to mean that the response in temperature isn't going to be equal either. There's lots of fluxes that we see with winds and sea currents. And so to really understand kind of where individual climates are going to land and where they're going to be shaped, we kind of have to understand how this heat gets transferred around the planet. Make sense? So far, so good?
Yeah, so far so good.
Okay. So one of the things, I want to play a short video, which is going to talk about, let me go ahead and share my screen real quick. First, this one. And we want this over here. So, so in Dr. Farous's PowerPoint, which, by the way, I sent out, and it's also on Moodle now. She brought up a few different slides that I thought were particularly important. I mean, they all were, but some that I want to focus on now, which gets at this idea of this variability on the planet, that it's just not all evenly spread. We know that there's variability with different altitudes, right? The higher you go, the cooler it's going to get. And that's why if you look at a mountaintop, if you go, over 4,600 feet, you reach the snow line, which is where most of the precipitation is going to come in the form of snow, because it's really, really cold up there, right? There's a limit to what height the trees can grow? Why do you think there's a limit to how high, what altitude trees can grow?
Um, would it be because the requirements of how much actual um oxygen they would be able to uptake? Would that have an effect the higher they are on the mountain? Would that kind of affect their ability to grow?
Is oxygen what plants use to grow?
I mean, I bet CO2.
Right. That's exactly it. It's the amount of CO2. So, um, CO2 is a gas, but it still has weight. It's still pulled by gravity. The concentration of CO2 is going to be greater the lower you are, and it'll be less as you move further away from the Earth. Um, and so when you're up at these really high latitudes, 3,600 meters to 4,600 meters, that's about kind of the limit of the amount of CO2 that you need for plants to grow. And if it gets any less than that, you're not really going to get a lot of photosynthesis going on. And so there's that limitation right there. And so that kind of tells us almost immediately why all of the layers below the tree line are going to be in warmer climates, right? Because remember, our favorite equation tells us that the number of layers helps dictate what the surface temperature is, right? And you can think of the more that we have of CO2 as more layers, but indeed it is kind of layered, right? So if you're below this tree line here, um, in this region, like between 1,800 and 3,600, you definitely have a layer of CO2 above you that can take in infrared radiation, absorb it, and then re-radiate it out into space and then back down towards you. So it's going to heat up um, uh, the surface region. That's why above the tree line, there isn't as much CO2. So it's a lot colder up there. There's no layer above it that's re-radiating infrared down on it. And so as you get lower and lower and closer to the surface, as you saw with when we started doing climate models with 2 and 3 layers of greenhouse gas, the temperature at the surface is going to increase because this layer is radiating down as well as this one, as well as this one, as well as this one. So in this case, 1, 2, 3, you've got a 4-layer atmosphere is kind of shown here, all radiating down a certain amount of infrared, which adds up. And that really makes our surface warmer. But it does mean that there's temperature differentials between high above and low at the surface. And because of that, we also know a couple other things about the behaviors of gases. We know that hot gases will be less dense because their molecules have more kinetic energy, so they're moving further apart faster. And so warm gases will rise, cold air will sink. That's something that we already all know, but that's going to give rise to a number of different effects that are going to affect wind patterns. I'm sorry, that's not wind patterns around the globe. Okay. And Dr. Ferrusa showed this nice graphic talking about Hadley cells and Ferrel cells and polar cells. I just wanted to go into a little bit more detail on what those are, so you kind of get an idea of why we're getting the different climate variabilities that we're seeing and the different climate classifications. So I'm going to share a video. Let's see, and hopefully you can hear the sound. Let me know if you can't. And let me move this out of the way, and this out of the way.
Look at the Earth. Isn't it beautiful? Blue oceans, white polar ice caps, and verdant green land. Some brown as well, where there aren't as many plants. But why are those parts of our Earth barren and others green? I mean, deserts cover much of Africa and Australia, but not Europe. Europeans, it turns out, discovered the answer, but in the most unlikely of places, the oceans. When sailing from Europe, trade winds pushed ships enthusiastically southwest to the equator, where suddenly the winds would die. These were the doldrums, and for sailors, they were a pain. They were also annoying to scientists like Galileo, Kepler, and Halley, who all had theories about why the wind blew to the southwest. Did the wind somehow follow the sun from morning till night? Or maybe it had trouble keeping up with the ground spinning beneath it. In 1735, a London lawyer and amateur meteorologist named George Hadley came up with an even brighter idea that ultimately helped explain not just ocean winds, but also why our planet has rainforests in a belt near the equator and deserts just north and south of that. Hadley figured that since the sun warms the Earth most at the equator, air to the north and south must be cooler, and therefore more dense. Just as cold air rushes in through an open door in winter, cool air north and south of the equator must flow toward the warm air in the middle, bringing sailors with it. There, in the doldrums, the air didn't actually stop moving, it just headed upwards, heat rising to make way for the denser air flowing in from both sides. And here's where the Earth's greens and browns come in. As warm, humid air at the equator rises, it cools, and since cool air can't hold as much moisture as warm air, it rains. A lot, enough to make rainforests. After reaching an altitude of about 17 kilometers, the rising and drying air hits the stratosphere, which acts kind of like a ceiling, causing the warm air to spread out and separate. Some goes north, some south. As the air leaves the equator, it rains away more moisture, becoming denser and slightly cooler, until finally dry, it sinks, creating the arid bands where many of the world's famous deserts lie. This giant atmospheric conveyor belt, officially called a Hadley cell, brings us both tropical rainforests and deserts, so the locations of the greens and browns of the Earth come courtesy of a lot of hot air.
I'm going to replay that one more time. Did you guys like that? I found it pretty illuminating.
Absolutely.
Okay.
Yes, sir.
Look at the Earth. Isn't it beautiful? Blue oceans, white polar ice caps, and verdant green land. Some brown as well, where there aren't as many plants. But why are those parts of our Earth barren and others green? I mean, deserts cover much of Africa and Australia, but not Europe. Europeans, it turns out, discovered the answer, but in the most unlikely of places, the oceans. When sailing from Europe, trade winds pushed ships enthusiastically southwest to the equator, where suddenly the winds would die. These were the doldrums, and for sailors, they were a pain. They were also annoying to scientists like Galileo, Kepler, and Halley, who all had theories about why the wind blew to the southwest. Did the wind somehow follow the sun from morning till night? Or maybe it had trouble keeping up with the ground spinning beneath it. In 1735, a London lawyer and amateur meteorologist named George Hadley came up with an even brighter idea that ultimately helped explain not just ocean winds, but also why our planet has rainforests in a belt near the equator and deserts just north and south of that. Hadley figured that since the sun warms the Earth most at the equator, air to the north and south must be cooler, and therefore more dense. Just as cold air rushes in through an open door in winter, cool air north and south of the equator must flow toward the warm air in the middle, bringing sailors with it. There, in the doldrums, the air didn't actually stop moving, it just headed upwards, heat rising to make way for the denser air flowing in from both sides. And here's where the Earth's greens and browns come in. As warm, humid air at the equator rises, it cools, and since cool air can't hold as much moisture as warm air, it rains. A lot, enough to make rainforests. After reaching an altitude of about 17 kilometers, the rising and drying air hits the stratosphere, which acts kind of like a ceiling, causing the warm air to spread out and separate. Some goes north, some south. As the air leaves the equator, it rains away more moisture, becoming denser and slightly cooler, until finally dry, it sinks, creating the arid bands where many of the world's famous deserts lie. This giant atmospheric conveyor belt, officially called a Hadley cell, brings us both tropical rainforests and deserts, so the locations of the greens and browns of the Earth come courtesy of a lot of hot air. Look at the Earth. Isn't it beautiful?
There we go. Okay. And stop sharing that. And go back to sharing this. Okay. So that leaves us back to this map, which kind of gives a little bit more reason behind why we see the dry bands that we do and the green bands that we do. And then here's, much of our different categories that we have for climate. Any questions on this? So on Moodle and in the email I just sent, there's a link to the next peer teaching, which is just going to be going through a climate classification exercise. There's a couple questions. There's a graphic there. If you haven't seen it, take a look. I can even go ahead and show what that graphic looks like. That looks like this. And so you're going to be given two graphs, and there'll be some questions on those graphs, and for you to try and figure out what some of these climate classifications are. And just refer back to the PowerPoint that goes with Dr. Faroosa's lecture to help determine what climate zones you're looking at. And when you make the video, kind of walk folks through how you're coming to those answers. So if somebody doesn't get what's going on, they can check your video and end up learning what you're talking about. But that graphic is up on the Flip site, and the link to get to that Flip is both on Moodle and in the email that I sent out. So you should have both of those. Now over here at Claflin, we are in our midterms week. So this is kind of like the middle of the course so far. And I've done most all of our assessments, on these peer teachings, right? But I want to give you a chance to kind of flex your muscle and remind yourself of different facts. So by Wednesday, I'm going to send out we can call it an exam, but it's an exam you can sit down and work on at home and then turn in. And I've got a series of questions based on all of the different talks that we've had so far. Want you to be able to explain certain concepts, and I can share some of those with you just so you can kind of see. But these are all things that we should know the answer to at this stage. So let me, things like the differences between climate and weather, what a temperature anomaly is, how it's calculated, what are the reference periods used for most climate data. Then I want you to know some numbers like the specific global temperature anomalies, both globally and then also in different regions. I want you to be able to explain what going down the up escalator is, that logical fallacy, some of the other records that support the surface thermometer records. I think you can all do this because in a lot of cases you've done this in your peer teachings, okay? But they are focusing specifically down on facts that I want you to know. Stuff about what satellites tell us about the troposphere versus the stratosphere, what the ice record tells us, what we know about the bulk ocean temperature, sea level rise, what paleoproxies are, what we know about paleo Earth and how temperatures have changed over time, when we're due for the next ice age, for example, and then some other things about these power relationships that we talked about, and what a black body radiation is, what causes it, why black body radiation is so important, and that kind of leads us into why CO2 is such an important gas, as well as what are some of the other greenhouse gases. Some questions about the albedo, what it is, what its actual number is, what energy balance has to do with climate change. What about water vapor? And then, so there's a lot of questions here, but I suspect that a lot of these will be hopefully pretty quick to answer. I'll give you enough time. That's why I'll give you this on Wednesday. It'll be due by Friday night. But it looks to be around 55 to 56 questions. And hopefully they can all kind of fit with what we've covered so far. And I may try, instead of doing new material on Wednesday, I may try and kind of sum up and put it all together, since we're at kind of a halfway point. Have you all been reading the book so far? And do you find that to be a good textbook? Like, do you like the textbook? What's your opinion of it? It's easy to read, hard to read. This is the first time I'm using that textbook, so I'd like to know your opinions.
It's a pretty much one-to-one. Following the lecture and following the textbook is pretty much the same.
Okay.
Same information, I would say.
Yeah, because all of the lectures that I've been doing really match the book fairly closely at this point. And I did that on purpose because it's easier, I think, in an online class to have a textbook that kind of goes along really well with what we're talking about. Although towards the end of the class, I'm going to diverge a bit because I really want to start talking about local variations and local predictions for climate change. And I'd also like to talk about biological adaptations and biological changes. You know, we're seeing a ton of different extinctions of species, and you know what that's doing to our environment. Why are we seeing all these extinctions, etc.? And our particular textbook doesn't really go into the biology of a lot of different species and biomes. And so I may share a couple articles with you in lieu of having the textbook when we get to those sections. There's a really neat section in the book. I'm not sure if I'm going to get to it or if I'll cover it at the end. It's let me look at what chapter it is. It's chapter 7. And in chapter 7, what folks look at is, so a lot of times when you hear people talk about climate change, they're trying to say, oh, it's due to something else. Oh, it's due to the variations in our orbit. It's due to, you know, continental drift, you know, all these different crazy things. That chapter really covers the facts on those things. And so if you want, I can do chapter 7 in a lecture, because it is handy to be able to refute those kinds of, you know, what people say. But the focus of this course isn't just on climate change and how to refute people who disagree with it. It's really on climate change, what exactly it is, what causes it, and then what effects is it having on our Earth. Because later on in the program, you know, we're going to be trying to teach you a lot of ways to mitigate some of these problems using biotechnology, using genetic engineering, using plant biotechnology, design of, you know, protein and enzyme design, like looking at biofuels, etc. All of these different specific adaptations, you know, to some of the problems of climate change. And so I really want to go over different regional things. And this is where I kind of want your input at this stage, because there's so many different biomes to talk about and so many different species that there's no way I could cover all of that in one course, at least just an hour a day, you know, 3 days a week. So if you could email me and tell me which biomes or species are of particular interest to you, I can make sure that some of those that I comprise some of that in what I cover. So you might be looking at biomes that are regional to you. you know, species that might be important in, you know, that you're curious about, or that's important in the biome close to you or somewhere else. If you work in a job in this area with a focus of what your job is going to be, there might be some good discussion there. So if you could shoot me off an email, and, you know, give me some ideas of the biology where you'd like me to focus on. I know there's a number of things I already plan to focus on, but I'd like to be all inclusive to make sure that the information you're getting is really helpful to your specific goals in your region. Okay. This is the point too where I wanted to ask, from all of the stuff that we've covered, and we've covered a lot of different things. I'm going to bring up all of our lectures here because it's a huge amount when I look back at it. So we've covered 19 lectures so far, from climate versus weather all the way up to climate classifications. And we've covered radiative forcing, climate sensitivity, the whole carbon cycle, how to do climate models, black body radiation, as well as, you know, all of the temperature records, and paleoproxies. Are there any questions you have? Anything you want me to go over that you're a little bit unclear on at this stage, or we're all good?
Probably can touch back on black body radiation and energy balance.
Okay, great. Because I want to do this before I give you all those questions to go through, right? The first thing to remember about black body radiation is why it happens in the first place, okay? So, let's see if I got a good, everything radiates black body radiation. It doesn't matter if it's really hot or pretty cold, it's still radiating. You might not be able to see it, but it's radiating. And hold on a second, let me bring it a little. See if I have a good graphic to help explain this. Let's see what kind of fun little graphic do we have. Don't know if I like that one. Let's see if I got a good one. Okay. Regardless if you've got a compound that's got a lot of atoms or it's got just a few atoms, when you heat it up, those atoms start to jiggle back and forth. In fact, that's our definition of temperature, is the average kinetic energy. And kinetic energy is the energy of motion, right? It's warmer something is, the more the atoms and the molecules move. Now, if it's a solid, what makes something a solid is that there's lots of interactions between the different molecules of the solid that pretty much hold them in place. And so that means that when you heat up a solid, those molecules that are packed in that solid, they'll start to vibrate and move a little bit, just back and forth, kind of like vibrating, maybe rotating. and just kind of moving around, but they're kind of held in place. As you increase the energy, eventually those movements will start getting bigger and bigger and bigger and bigger until finally you overcome whatever forces were kind of holding them in place, and then it becomes a liquid. So now the molecules are moving around. They still have some interactions in between them, but much fewer, and so they have a lot more movement. You still heat them up further, you get more kinetic energy, they move faster and faster and faster until finally the amount of energy they have is enough to break whatever last few interactions between molecules there were, and each molecule is now free of interactions with the other molecules around it, and so now it's a gas, and they can fly wherever. And you can still heat up the gas, which means that the atoms move faster and faster and bounce around, and so they still have more kinetic energy. So that's what temperature does, why we have our 3 states of matter. Technically, it's 5 states of matter, but we won't get into that. One has to think about what makes up an atom, though. Remember, atoms have 2 parts. They've got a nucleus, and then they have an electron shell around it, right? Where the electrons kind of reside. And whenever you move something that has an electric charge, when you move it, that creates a magnetic field, okay? This is how we make motors. You pass a current through a wire, that creates a magnetic field. You can use that to turn a magnet, which then gives rise to motion and gives us a motor. You can do it in the reverse. You can generate electricity by taking a magnet and moving it around a coil of wire, causing electrons to move and create an electric current. And so there's always this, whenever you have a moving electric current, you have this magnetic field. When you stop that, or there's a fluctuation, an energy change, that energy's got to go somewhere. And so that energy can leave in the form, since it's electromagnetic radiation, electromagnetic energy, it can leave in the form of a photon. The amount of energy of that photon determines its wavelength. And so high energy photons have very short wavelengths, low energy photons have very long wavelengths. And so, we started looking at, where's our spectrum of ultraviolet energy? And so whenever you have atoms moving, they're going to be vibrating, generating electromagnetic energy. Some of this will be leaving as photons. The wavelength of the photon is just going to be determined by how much energy you're dealing with at the time. And that's related to how much kinetic energy, right? And so since we equate kinetic energy with temperature, that means that the temperature that the body is at is going to be proportional to what wavelength of light it's going, or photons, electromagnetic radiation, that it's going to release. And it just so happens that things at around room temperature and in the temperatures that we normally dwell in, the energy of those photons are in this infrared region over here, right next to the visible spectrum, but not quite visible. You have to get really, really, really high, around 4,000 to 5,000 degrees Celsius, before you start emitting, before the photons that are being emitted are in the visible light range. And so we came up with, we discussed Wien's displacement law, which tells you what the peak wavelength will be. And we know that it's just a peak, right? Whereas there's a peak, there's also a lot of other wavelengths that it covers. And like for this example, in a stove, when you're really, really hot in a stove, you might start emitting some light in the visible range, but most of it's going to be in this infrared. And that's what we call this black body radiation. And so we can't see it because it's not in our visible range, but it certainly is radiating around us. And so we shine the light on the Earth, it heats up. When it heats up, it's now radiating that energy back out. And because of the temperatures we're at, those photons are in the infrared range. If we were hotter, it would be in the visible range. If we were cooler, it would be in the microwave range. Okay. But we land smack dab in the infrared range. Why is that so important? It's important for two details. One, most of our atmosphere is composed of oxygen, nitrogen, and argon. And all three of those elements, don't absorb light in the visible range at all. So light can pass through them without being absorbed at all. They can reach our surface, which has things of different colors, which can start absorbing those photons. That will heat up the surface. And then when the surface re-radiates, it's not re-radiating in the visible range anymore, like we just discussed, but for black bodies and our general temperatures, it's re-radiating in the infrared. And why is that so important? Well, it's really, really important when it comes down to, let's see, carbon dioxide and some of the other things in our atmosphere. So if we look at, go back to our atmosphere, we know that water vapor is a big component of the atmosphere. CO2 is not a huge component, only about 410 parts per million right now, but it's significant because CO2 happens to absorb. So this is the absorption spectrum for different gases. And notice oxygen really isn't in here, ozone a little bit. Straight nitrogen's not here, argon's not here. So none of the other components of the atmosphere really absorb in the infrared, but carbon dioxide does. And so that means when you have CO2 in the atmosphere, it's going to absorb that infrared radiation. And why does CO2 absorb more than other things? Why does it have this particular absorption spectrum? That just has to do with how these things bend and stretch. All atoms absorb energy based on their stretching and bending modes, and they do it at certain frequencies. And it just so happens that a carbon with two doubly bonded oxygens will have frequencies to their bending and stretching that fall within the infrared range. So some are IR active, like these different modes here, and some are not IR active. And so this molecule just happens to absorb, which means it's going to absorb the energy, and it too is going to act like a black body and have to re-radiate that energy from those motions. Does that kind of answer your question on black body stuff? You know, we have formulas that tell us what our peak radiation will be, you know, what our peak wavelength will be. And then we have formulas that tell us how much power is coming out from that object. And our formulas, like the Stefan Boltzmann, is usually power per unit area, which is actually really helpful. Now, if we had a specific object, you'd have to know its surface area to know exactly what the total power being emanated is. But a lot of our calculations, when we're doing climate stuff, We're just interested in power per unit area because we're talking about the sun shining down on the part of the surface of the earth. And so we often do it in power per unit area. And so black body radiation then is just really how much the planet is re-radiating up once it heats up, and then the atmosphere itself, how much is it going to radiate both out into space and down back onto the planet. Are there other questions in terms of topics that we've covered so far that you'd want some additional explanation?
Hello, Doc.
Yeah.
Yeah. So I didn't quite really understand the topic where you talk about carbon dioxide, especially how it is emitted into the atmosphere from rocks.
Oh, okay. So we're talking about the carbon cycle, right?
Yeah.
Okay. So with the carbon cycle, so we first talked about CO2. One of the first things we mentioned about the carbon cycle was the seasonal variations, right? And we found that those were due mainly to two things: photosynthesis, that's going to pull up CO2 out of the atmosphere, and then respiration, which is the reverse of photosynthesis, and that's going to put CO2 back into the atmosphere. And so we have this initial carbon cycle between the land biosphere and the atmosphere. So the plants and animals doing photosynthesis and respiration. It's not just animals. When something dies and there's bacteria and fungi that start to break down the decomposed body, that's respiration as well. Also, we generate some methane from that, which is more carbon in the air. So we've got this first part of the carbon cycle. The next part of the carbon cycle is the land-ocean atmosphere. So if I can find a good graphic here. And that's the fact that the atmosphere will exchange with the ocean, in that CO2 is highly dissolvable or soluble in water. And when CO2 dissolves in water, it makes this carbonic acid. And so a lot of CO2 will be absorbed by the ocean, causes the ocean to be more acidic. The ocean will also degas, and this reaction can happen in reverse, where carbonic acid can turn into water and CO2, which leaves as a degas. And so you have this carbon cycle. Now, it's important to know with the ocean that the entire ocean isn't really all the same. The first 100 meters of the ocean is what we call the mixed layer. And it has about 900 gigatons of carbon in it. In a lot of cases, it's between ocean life and dissolved CO2. But below the mixed layer is the deep ocean, which has way more carbon in it, 45,000 gigatons. 97% of the ocean is the deep ocean. But there's this slow exchange rate between the ocean mixed layer and the deep ocean. And so this becomes part of our overall carbon cycle. We've got photosynthesis and respiration happening between the land biosphere and the atmosphere, and then the atmosphere is also dissolving into the ocean and degassing out of the ocean. Sorry. But that's still only part of our carbon cycle. There's also the rock cycle, which is the weirdest one out of all of them. So we've got this up a little bit. All of this stuff also exchanges with the rocks. And that kind of seems kind of weird to say. But when you think about it, at least going from rocks into the atmosphere, that one actually is not as hard to understand. We're talking here about volcanic eruptions. And this causes about the release of about 0.1 gigatons of carbon per year. When there's a volcanic event, it releases lots and lots of CO2 and methane into the air. And that's how we get basically from the rock layer going into the atmosphere. Now, how did the rocks have this carbon to begin with? Well, it's carbon that's been buried in the ground and is erupting. Now, certain types of rocks have carbon as part of their chemical structure. Matter of fact, many, many rocks do. We can go over some of those. So silica is calcium carbonate. It's CaCO3. If this is in the rocks of a volcanic region, when the volcano explodes or erupts, it'll be hot enough to break all these chemical bonds and release that carbon into the atmosphere. Okay. So there's lots of different rocks that have, you know, there's magnesite, that's magnesium carbonate. It's got carbons in there. There's dunite. There's all sorts of different things that have this carbon in these rocks. And so you can get, during volcanic eruptions, this carbon is released into the atmosphere. So that gives us volcanic eruptions. Now, in the opposite direction, going from the atmosphere to the rocks, is something we call chemical weathering. So remember that CO2 readily dissolves into water, forming carbonic acid. Well, this happens in raindrops too. When the rain is falling from a cloud, CO2 in the atmosphere dissolves into the rain, making it slightly acidic. And then when you've got this slightly acidic water hitting a rock, dropping from, you know, thousands of feet, it's got a lot of energy as it hits. That's usually enough to create chemical reactions. Okay. So if you've got calcium silicate, for example, and these raindrops with CO2 with carbonic acid hit them, it can cause a chemical reaction which creates limestone or chalk. This calcium carbonate here. And this actually occurs, but it occurs over geologic timescales, over very long timescales. And so there's a lot of different chemical reactions that happen with this carbonic acid that's in the water. Remember, it can go back and forth into CO2, and these elicit these kinds of chemical reactions. So we get limestone deposits. These limestone deposits, you know, in parts are huge deposits of carbon in the rocks, part of the rocks. Okay. You get a lot of carbon storage in limestone. You can also get it in some of these other rocks. Dunite will turn into magnesite, which has lots of carbon in it. Basalt will turn into dolomite and calcite, different kinds of rocks that have carbon as part of their chemical structure. And so this gives us, you know, another back and forth into our carbon cycle. We had the land, biosphere, atmosphere. We then started adding the oceans in the mixed layer. And now we have volcanic eruptions, which are erupting carbon into the atmosphere, and chemical weathering, which is pulling it out. And then there is a third way of getting, or second way of getting carbon out of the rocks. And that's, you can have organic material in the land biosphere that gets buried and never gets a chance to decompose and be broken down through respiration to be CO2 in the atmosphere. And it just gets buried and pushed down. And the high heat and the high pressure tends to create a lot of these double bonds. There are dehydration reactions that pull out water molecules. So buried under the ground, that organic material becomes these long hydrocarbon chains. And that's where we get coal from. It's where we get, I mean, if you look at what coal is, that's just cellulose that's been treated with pressure and temperature and dehydrated into these long carbon chains. That's coal. You can do that with stuff on the bottom of the ocean, stuff that's falling in the bottom of the ocean, gets covered with more sand and silt, and eventually gets crushed down again into these long hydrocarbon chains, which is where we get our oil and gas deposits from. And basically all these things are just long hydrocarbons. And so this gives us our last part of our carbon cycle, which is now the burning of fossil fuels, which is what's driving our current warming, because now we're taking these things out of the rocks, burning it and putting it back into the atmosphere. Normally, the only route back into the atmosphere from the rocks is volcanic eruptions, which should only be about 0.1 gigatons a year. But we're doing many gigatons a year and burning hundreds of gigatons a year in the burning of fossil fuels. And so this is where we now have a problem, because we're pumping lots more in. Does that answer your question? Brenda?
Yes.
Okay,
I
good.
really need the clarity on the burning of fossil fuels.
Yeah, it's because it's happening at such an increased rate, much faster than it should, that we're having a big problem. Okay, this is a good place to break. I'll see you again on Wednesday, and I'll be sending you out those questions shortly.
Sorry, Doc, just out of interest sake, we were discussing lately about the atmospheric layers and in that lecture of climate models. I just want to know that currently at the moment, how many layers are they?
Oh, you're talking about how many layers. So that's related to the amount of greenhouse gases. The actual number, and we'll go through how that's derived, but I think the actual number is like 3.2. And I'll show you later how that's kind of arrived. Just remember from our formula, knowing that, and all I really need you to get out of all that right now is that the more layers you have, the warmer it's going to be on the surface.
Yes.
And then we're going to equate these greenhouse gases with having more layers.
Yeah. Okay.
Okay. Thanks a lot. Oh, there's a question in the chat. Okay. Desire, are you saying that you don't have all the PowerPoints? Yeah, I can send you a link that's got all of them. If anybody's missing some PowerPoints, let me know, but I'll try and send a link out to all of them.
Thank you, Bob.
Okay, thanks a lot. Have a great day.